Okay, so here we've got an integral of e to the x cos x dx. We know that the integral of e to the x is equal to e to the x plus a constant. We know the derivative of e to the x is e to the x. So what I'm going to do here is we'll let u equals cos x. So u dash is equal to minus sin x. And v dash is equal to e to the x, because to make that, it's easy to find v. And the integral of e to the x is just e to the x. So we'll quote our integration by part rule. U v dash dx is equal to uv minus the integral of u dash v dx. So the integral of e to the x cos x dx is equal to my u is equal to cos x times v, and v is equal to e to the x. I'll put it first, cos x, minus the integral. Now u dash is minus sin x times v. V is equal to e to the x dx. Minus, we can make it into a plus, so we've got e to the x cos x plus the integral of e to the x sin x dx. Now that is no simpler than e to the x cos x, but what we can do is apply the rule again and see what happens. So we'll just apply the rule one more time to this. So in the second one, now we made v dash e to the x, and it's important that we'll make v dash e to the x again. So we'll let u equals sin x. So we've already used little u and little v. So u equals sin x. So u dash, derivative of sin is cos, and v dash is e to the x. So v, the integral of e to the x, is simply e to the x. So just looking at this second integral here, we can say that the integral of e to the x sin x dx is equal to uv. So we'll put e to the x in front of sin x, better way to write it, minus the integral of u dash v. So u dash v, so e to the x cos x dx. And you start saying, well, maybe we're just going around in circles, because we're back to where we started from. This is exactly the same as where we started from. But that's, in a way, that's a good thing, because what we'll do is we will substitute in here for e to the x, the integral of e to the x sin x dx, and you'll see what happens. So putting it all together, we've got our original integral that we're asked for, the integral of e to the x cos x dx is equal to e to the x cos x plus, now this integral here we've just worked out as e to the x sin x. So this one here is equal to e to the x sin x minus the integral of e to the x cos x dx. Okay, my next move, we're trying to find this, and we've got it there, and we've got it there. So if I bring it over, this one here, bring it over to the other side, the minus become a plus. So I've got integral of e to the x cos x dx plus the integral of e to the x cos x. So if I've got one of them plus another one of them, I've got 2 integral e to the x cos x dx is equal to e to the x cos x plus e to the x sin x and there should be a constant of integration there as well. Now we can divide right through by 2. If we divide right through by 2, every term has got to be divided by 2. So we've got dividing by 2. So we're going to divide all of this right through by 2. Dividing by 2 there, we just get the integral of e to the x cos x dx equals, divide this term by 2, e to the x on 2 cos x, plus divide this term by 2, e to the x on 2 sin x, plus c on 2. Common factor here is e to the x on 2, so I've got e to the x on 2 side of cos x plus sin x plus k. K is equal to c on 2. So it's just a constant of integration. So summing up there, this process involves doing integration by parts twice, but rather than it look as though you're going around in circles, if you can get back by the second or third time you do integration by parts to the original integral that you're asked for, you can put it all together and you'll have a minus there. That, when it comes over, becomes 2. Divide right through by 2 and we'll get our answer.